Now let's look at gain control in the efficient spatial coding. Gain control is the second step in the efficient coding process. In the first step, decorrelation, it transforms the spatial image into its Fourier components, SK1, SK2, etc. These components are now decorrelated from each other. We have seen that these components have the highest power at low spatial frequency, K, and decays very quickly with spatial frequency K. The next step is gain control. For each Fourier component, you add a gain to it, and this gain value is, let's recall, it's according to this formula. Yeah. In particular, it depends on the signal to noise in each Fourier component. So when signal to noise is high, this gain is stronger for weaker signals. Okay, and this is for whitening. When the signal to noise is low, this gain is stronger for higher signals in order to smooth out noise. Yeah, and so therefore at each spatial frequency, you have to see whether how high is the signal, how high is the noise. Yeah, to see whether it's high or low signal noise for each frequency. We plot the signal power and noise power together in the same plot. In natural scenes, the signal power decays with frequency k as 1 over k squared. However, because the image noise in different pixels are not correlated with each other, noise is white noise. This means that the noise power is a constant, independent of frequency. And so therefore you see in this region, in this small frequency, you have the high signal to noise. Signal is much higher than the noise. In high frequency region, the noise dominates, and here it's where they are comparable. So this is where we mark as a transition region at frequency Kp. Okay, so therefore, if you look at this formula, you will see the gain as a function of frequency should look like this. So in this high signal to noise region, the gain should increase with frequency, because at low frequency the signal is high, the gain should be low, and as it increases the signal drops down, the gain should be high. Okay, and this is whitening, and whitening means in this region the output should be almost, the output power here, yeah, it should be almost independent of frequency. And also in this region you can see that by being low, you are trying to ignore the DC, DC, that means the average of the images, okay? And then you become more and more sensitive as the frequency becomes higher. That means as the spatial variations, these pixels change with space a lot, so you make it more sensitive to any spatial change. That's the contrast. So you are trying to enhance contrast. Now at the high frequency region, the signal noise is so low, you don't want to transmit too much power. The noise power dominates over the signal power, so the gain should immediately cut down. Yeah, and this also means the output power should also cut down. Yeah, and so therefore this gain is rising up, peaks in this sweet spot, intermediate frequency, depending on the signal noise, and then drops down. Yeah, and so this is a bandpass filter with low gains for small frequency and high frequency, and highest gains in this band. So now let's visualize this G curve. Okay, this G curve is also called the contrast sensitivity curve. So by this image. Now in this image, horizontally, frequency is increasing. That means this, image pixel value changes slowly here because the frequency is low, changes faster with space, frequency get higher. Okay, along the vertical axis, the image contrast becomes stronger and stronger. You see here it go white to black in a big magnitude and gets smaller magnitude and even less small magnitude. And so when it's getting very, very weak changes, you can't see it unless your sensitivity is very high. As you can see that here, slowly you can't see change anymore because the gain sensitivity is not so high. Somewhere in the intermediate region where your sensitivity is higher, you can see all the way this grating change is quite high. But as the sensitivity drops down, again, you cannot see it. So you can visualize where you peak, okay, for individuals. Of course, this also depends on how bright the environment is. But you can see the bandpass filter just like that, yeah. Since we give one gain to each Fourier component, this gain control stage is this diagonal matrix G. Now remember that the Fourier transform K0 is this n by n matrix. Therefore, if we combine these two first stage together, we have this matrix as the product of these two matrices, and it transforms the original image pixel vector to these gain-controlled Fourier components.